All right, hi everyone. Thank you for coming out. I know it's the last day of the conference and everyone might be a little tired, but I appreciate you coming. And thank you to the organizers for putting this on. This is the first RubyKaigi I've been able to attend in 4 years, and it's great to be back. For those who don't know me, I'm a staff engineer at Shopify. I've been there just about 2 years, but I've been working with Ruby for the last 15 years, and a theme I've had during that time is working on performance. I've worked with Ruby Enterprise Edition, JRuby, Truffle Ruby, and so on. And I think what's great about a VM like Ruby is if we can fix performance in the runtime, then applications just get faster for free. So individual application developers don't need to spend time trying to work around deficiencies in the VM. Their end users get a faster experience. And ideally, there's even an environmental impact as we're able to do more with fewer resources. In 2014, I turned that into a full-time position when I began working on Truffle Ruby. I did that when I was working at Oracle Labs, and I'm continuing that work now at Shopify. Truffle Ruby was founded in February 2013. We had the tragic passing of our founder, Chris Seaton, last year, which put a little bit of a damper on the celebrations, but we have hit our 10-year anniversary. There have been many people that have contributed to the project, and I think we've been beneficial for the Ruby community. We try to provide tooling that makes it easier for other people to also optimize Ruby in different ways. We're big contributors to the Ruby spec suite, which is really helpful for people trying to build new Ruby implementations. And Truffle Ruby's been a pretty good test bed for trying different ideas out, like object shapes, which have managed to make their way into C Ruby. I've spent a lot of time looking at string performance. Strings are one of these things where a lot of people think they're just kind of a display characteristic, so they don't need to be fast. But we use them a lot, particularly in the web application domain. So we'll use them for generating web responses, email processing, even log output. And what happens behind the scenes is there's a ton of different concatenation operations or string interpolation. And if we can speed those up, then we can generate responses quicker. It's also really useful for APIs. So we know that binary-based APIs generally can be more efficient both in memory and performance, but they're a lot harder for developers to work with. So REST and GraphQL largely use JSON as the interchange format, and we want to make those fast as well. Configuration data is another area. Traditionally, we haven't put a huge emphasis on this because it's usually done at startup. But what functions as a service, we want to start the process as quickly as possible. In Ruby, we have another aspect, though, and that's metaprogramming. Now, all these various metaprogramming calls take strings as arguments. They'll also take symbols, and if you can use a symbol, that's generally more efficient. But if you're working with dynamically generated data at runtime, it will probably be a string. One of the things we worked really hard on in Truffle Ruby is eliminating the overhead of metaprogramming. And this was something that people largely thought wasn't doable, that if you wanted this rich, expressive functionality from the VM, you were going to pay a performance penalty for it. But we in the JIT compiler have basically eliminated that overhead. But in order to do that, we had to put a lot of emphasis on string performance. So the title of this talk is Rethinking Strings. I'm going to run through some of the string history, what the API looks like today, how it sets up new Rubyists for failure in different ways, and how it can limit performance. But really, I want to stimulate a conversation about how we might be able to advance strings for Ruby going forward. So I've been involved in 3 different string implementations in Truffle Ruby. And I've also looked pretty extensively at string implementations in C Ruby, JRuby, and Rubinius. So a lot of this talk will be kind of informed by my background there. The first approach to strings in Truffle Ruby was a pretty straightforward port of what C Ruby does to Java. Truffle Ruby is predominantly written in Ruby, so we did import some code from Rubinius and ported some of their C++ to Java. But for the most part, we were taking C Ruby's C code, turning it to Java. And that got us a high degree of compatibility, but we discovered along the way that it didn't work well with a JIT compiler for the sort of idiomatic code we wanted to optimize. So we rewrote the string implementation using something called ropes, and I presented on this at RubyKaigi back in 2016. While some of the details have changed, the emphasis and the core aspect of that still is the same. So the key difference is with the previous ByteList-based approach, you're dealing with contiguous regions of memory. So if you want to do a string concatenation, what you do is allocate a new buffer, and then you do memory copies from the two strings. And if you're doing many concatenations in a row, you're constantly doing these allocations. Now, there's some tricks behind the scenes where we can over-allocate some spare capacity to reduce the number there, but that's the key difference. It's going to be a linear time operation. With ropes, we still have contiguous regions of memory at leaves, but then we build up a tree of lazy operations. And this worked really well for some of the stuff we were looking to optimize, like ERB used to do a ton of different concatenations. It's since evolved in the time and does a lot fewer, but we had a huge performance benefit doing this. The other kind of salient detail about ropes are that they're an immutable, persistent data structure. And this seems a little paradoxical because Ruby strings are generally mutable, but by using an immutable representation, we're able to cache and pre-calculate certain pieces of information. So every string in Ruby has this value associated with it called a code range. And I'll get into what those are in a little bit, but the key point is they require a linear time scan to figure out what the value is, and any modification to that code range could possibly change it, requiring another linear time scan. Likewise, if you want to get the length of a string, you have to do a linear scan. With ropes, we were able to pre-calculate these values, which meant two things. One, if we needed to derive a new value, we could usually do that in constant time. And two, because they were constant values, they worked really well with the JIT compiler. The big deficiency, however, is strings in Ruby have this byte-oriented API. So the pathological case is you modify every single byte in the string, and with a rope, we have to allocate a new node for each of these cases. It's not great for memory, and it degrades to a linked list, which isn't good for performance. So last year, we re-implemented strings in Truffle Ruby again. This time, we've taken more of a blended approach. So we now support both a ropes-based representation as well as a mutable byte array. We haven't taken full advantage of this yet, but this will allow us on a per method call, and ideally per call site basis, determine which representation works best. Along the way, we also picked up some additional storage strategies, which will allow us to represent strings more compactly, and it makes it more efficient for us to do polyglot applications on the GraalVM platform. All right, so I'm going to talk a little bit about the string API, but it's helpful to remember that Ruby's a 30-year-old language, and none of this stuff was really designed in a vacuum. A lot of it was very organic. So while I've been working with Ruby for 15 years, I got started with Ruby 1.8. I wasn't really involved with the core team or what was happening on the bug tracker. So I don't have the context for why some changes or decisions were made. So I tend to refer back to this copy of the Ruby programming language. I've had this book since 2008, and it is the only Ruby book I use. I reference it quite frequently. What's interesting about it, though, was it was written when Ruby 1.8 was the predominant released version, and Ruby 1.9 was still in development. So the book covers both pretty well. So in there's a passage about the difference between strings in Ruby 1.8 and 1.9. The key takeaways are that in Ruby 1.8, strings are a sequence of bytes. They don't have an encoding. To the extent that there was one, it was assumed to be ASCII, or it would be binary. If you wanted to use something like UTF-8, you needed to use a third-party library that then implemented it in Ruby, which wasn't necessarily great for performance and could introduce compatibility problems. With Ruby 1.9, there was a massive shift in how strings work in the language. They became a sequence of characters instead of a sequence of bytes. Ruby doesn't really have characters, but you can think of them as being strings of length 1, and they became encoding aware. This was a huge shift, but there was a compatibility concern here. How do we ensure all these Ruby 1.8 applications continue to work in the new 1.9 string world? So the string API today is kind of large, and I think it can largely be broken up into two categories. We have a text-oriented API, and this is where you can do like substrings or upcasing, capitalizing, and so on. And then there's a byte-oriented API, and a lot of this is what we had in Ruby 1.8. You can do direct byte manipulation, you can do byte slicing. There have been some additions to this in the time since, but for the most part, it's what we had in Ruby 1.8. The surface area of the string API can be a little daunting for new Rubyists, though. They're not sure which ones to use. Is the text-oriented one the more modern API? Is the byte-oriented one the more performant one? Which one should I use? So strings today in Ruby are interesting. They are incredibly complicated under the covers, but Ruby has done a remarkably good job of hiding that complexity and providing a very flexible representation. The API itself provides both immutable and mutable operations, so you can program in a functional or an imperative style, depending on what you prefer. You can freeze strings and get additional optimizations from the VM that way, or you can mutate them in place. Most languages really only support one or the other. Take a language like C, you have mutable strings and that's it. Take a language like JavaScript and all strings are immutable. If you want to mutate something, you allocate a new string. On top of that, strings in Ruby are encoding aware, but again, unlike other VMs or other languages, Ruby does not force an internal encoding. If you work with JavaScript, every string is going to be UTF-16. If you work with Rust, every string is going to be UTF-8. These languages do allow you to represent text in other character sets, but you need to handle the transcoding yourself. Ruby does not force that on you. You get to pick what the default internal encoding is. You can configure that at the VM level when you start it up or at runtime. You can override it on a per file basis, and you can change it on a per string basis. So interestingly, Ruby can have strings with different encodings floating through the system. Now, generally, encodings aren't necessarily compatible with one another, and you can't just take two strings with two different encodings and combine them. So Ruby goes a step further and tries to determine if an operation would be safe, and if it is, it will proceed to do it for you through an automatic encoding process or transcoding. All right, so it'll help a little bit if we take a look at encodings now. If you're not familiar with encodings, they're basically a way of turning bytes into characters. So every encoding has something called a character map, and you could think of it as a table where you use a lookup or an index called a code point. So each code point is defined to be represented in some way. The encoding is a sequence of bytes. So we can call encode on that sequence of bytes, and we get back as a code point. Now, sometimes a character requires more than one code point, so we'll have a secondary encoding function that will take a sequence of code points and turn back a character. And if you just compose these, you can basically map bytes directly to characters. So to help solidify this, here's a situation where we have 2 bytes and we pack them into a string. And using 2 different encodings, we get 2 different characters. In UTF-8, you get the copyright symbol. In Shift.js, you get something else, but they have the same underlying bytes. What's changed is the mapping to the characters. Ruby ships with over 100 encodings. This is a massive difference from other languages that force everything to be a single encoding. This complicates the VM because it needs to try to handle all these different encodings. On top of that, these encodings can have aliases, so there are 175 different ways to encode a string, essentially. With that said, Ruby tries, again, to hide a lot of this complexity, so we have default encodings. So most applications really only use 3 encodings. They'll use the default one for strings, which will generally be UTF-8. In certain circumstances, the VM will downgrade a string from UTF-8 to US ASCII, which is a simpler encoding. This will happen if you convert a symbol consisting of only ASCII characters to a string, or take a number and turn it to a string. And then there's a third encoding called ASCII 8-bit, and this will be used for I/O. So that ASCII 8-bit one is kind of an oddball. It's unlike any of the other encodings inside of Ruby. The name is a bit misleading. So a lot of people that don't really look into the internals of Ruby assume that this encoding is some variant of ASCII. But the actual ASCII encoding is US ASCII. So all ASCII characters are defined to fit into 7 bits. So the ASCII 8-bit name seems to suggest that there is some variant of ASCII that supports 8-bit characters. Now, historically, there have been attempts at having 8-bit characters that extended ASCII, but none of them are an ASCII 8-bit. They're all different names, and that's not how they work in Ruby. If we look at the aliases for this encoding, we'll see one is called binary, and I think this is a much more accurate representation of what this encoding is used for. It's intended to be used for binary data. So it's the only encoding in all of Ruby that doesn't map to characters. What trips people up, however, is this encoding reports itself as being ASCII compatible. So if you take a string that consists only of ASCII characters, convert it to a binary string, and ask if it's ASCII only, you get back the value true. If you look at the encoding, you get back the name ASCII 8-bit. So this kind of sequence of events confuses people. They think, okay, this isn't binary, it's some variant of ASCII. All right, so I want to get another topic here, the code ranges thing I kind of mentioned before. So working with an encoding like UTF-8 can be a little complicated because in UTF-8, every character can take up between 1 to 4 bytes. So if you want to hop around using like the string index operator, Ruby needs to figure out the individual character boundaries. If you're working with only ASCII data, then every one of those characters will be a single byte wide, and the VM can optimize for that. So Ruby will scan the string, start to finish, and record some information about it, this code range value. Every string starts off an unknown, so we don't know anything about it. They're lazily computed. Then there's CR7-bit, and that basically means it consists only of ASCII data, and the encoding is ASCII compatible. Then the next level is valid, and that means it's not 7-bit only, but the bytes actually have meaning with the associated encoding. And then there's broken. And this is the case where the bytes and the encoding don't match up. They won't actually yield characters. The code range value isn't exactly exposed in Ruby, but you can figure it out using 2 functions on string, asking if something's ASCII only and asking if it has a valid encoding. All right, so now I want to take a look at binary data. So Ruby as a general purpose programming language needs to be able to work with binary data. We work with images, want to take thumbnails. We compress strings. We read tarballs and whatnot from disk. So how can we represent that binary data? Because Ruby doesn't really have a data type for that. So one way to think of it is, well, bytes are just integers in a very narrow range, so we could work with an array of integers. And this will work, but it's remarkably inefficient because Ruby doesn't make any guarantees about how many bytes an integer will take up. So here, a megabyte of bytes actually takes up 8 megabytes of memory. The API will allow you to work with that, but you'll trash cache lines and you're going to bloat memory. So someone had the idea of, well, why don't we just use that sequence of bytes that Ruby 1.8 strings were? And in fact, you can do that. If you take a megabyte of ASCII characters, it will take up roughly a megabyte of memory. There's some additional overhead for the string metadata, but it'll work. But this is a leaky implementation detail. Ruby shouldn't be guaranteeing a particular representation or memory layout for strings. Moreover, you get into some kind of confusing situations. So here we're going to compress a string using zlib, and what we get back is a string with the ASCII 8-bit encoding. It does not consist only of ASCII-only characters. It is valid, so every string in ASCII 8-bit is trivially valid. You can't have a broken byte representation because there is no character mapping. But we can do things like take this compressed string and split it up into lines. Now, there really aren't any lines, but because it happens to have the same byte for an ASCII new line, Ruby happily splits it. Or we can do something like get the string successor. Now, this is a nonsensical operation, but Ruby just allows you to do it because those strings report as, that encoding reports as being ASCII compatible. So critically, like binary data and strings just are not logically equivalent. But in Ruby, we've forced developers to treat them as if they are. And this trips up people in other ways. So here we'll allocate two strings, one using an empty string literal, one using the string constructor. We can check, and they are indeed equivalent. Now we'll append a byte to each of them. So we'll append the hex value 80. If we check if they're equivalent, they no longer are. So what's going on here? Well, if we look at the bytes, even though we only appended a single byte value, the first one now has 2 bytes, whereas the second one has a single byte. So the core problem here is that string new and the empty string literal are not equivalent. And most Rubyists I talk to don't realize this. String new will allocate a binary string, whereas the empty string literal will allocate using your default encoding, which will generally be UTF-8. The second part that trips people up is this append operator, or the shovel operator, doesn't really take byte values. It takes code point values. So in UTF-8, the integer value corresponding to the hex value 80 refers to a code point that is represented with 2 bytes. And that's why that one has 2 bytes, but when we're working with the binary string, it only has a single byte. And I see people trip this up a lot of the time because they'll allocate a string buffer the way they're accustomed to using an empty string literal. And as long as the data you're allocating is ASCII only, it'll appear to work, but then it will fail in catastrophic ways later. So we now have this IO buffer class, and I think this is a remarkably good step in the right direction. But it's under the IO namespace, which I think confuses people into thinking it's really only usable for IO. Some of the API for it is indeed IO oriented. So we have other use cases in Ruby for working with binary data that aren't IO related, and it can confuse people if this IO buffer is applicable in that case or not. But the 2 major problems I see with it today, and I think these are fixable, are that it still relies on having binary strings in the system, and we don't exactly expose these to end users. If you call file read with a number of bytes, you don't get back an IO buffer, you get back a binary string. All right, now we have one specific code range value, broken strings, that I want to look at. All right, so again, a broken string is a string that the bytes have no meaning whatsoever with the underlying encoding. This is, again, kind of unique to Ruby. If you work with many more modern languages, you can't have invalid strings. The VM just won't let you create them, and then when you perform operations like upcasing or capitalizing things, they're well-defined operations. The result will always be a well-formed string. But there are situations where Ruby will hand you a broken string, and there are other cases where you can break a string yourself. So here's another failure case I see come up. Here, someone's reading a binary file, in this case an image, and they're using file read. Here, they're using the variant that doesn't take a number of bytes, or they're not working with a block. And what they get back is a string that's in UTF-8. It's not ASCII only, as we would expect. But if you try to upcase it, you get an exception because the string is broken. And we can verify that by checking whether the encoding is valid. The problem here is this should have the binary encoding, but it has UTF-8. Confusingly, we can force the encoding to be binary. This won't change the underlying bytes, and now we can upcase it. But that is an operation that doesn't make any sense for binary encoding. So that's a case where a broken string will break if you try to perform an operation. Here's another case where it won't break, it will just return a value that doesn't make any sense. So here we're taking a multi-byte UTF-8 string, changing the encoding to US ASCII, and if we check the size, it says 5. But that isn't an answer that makes any sense. Compounding the issue, broken strings that still return a value may return a different value depending on where the broken byte appears in the string. So this is really an implementation detail that's leaked out. It shouldn't be anything anyone relies upon, but developers have, and that limits our ability to do something differently there. All right, so can we fix any of this? I think we can, and I have a few proposals for Ruby 3.3 or beyond. As a caveat, we care a lot about backwards compatibility. So what I'm proposing here is more of a phased-in approach. Whether it's a command line flag we pass that allows you to opt into the behavior, I think we can start with warnings, maybe start raising exceptions, and find areas in the application that are broken that we can fix. I'd even be happy with deprecations, but we never actually remove the method, because these at least tell a developer that, hey, you should not be doing that thing. So one is, let's just invert the name ASCII 8-bit and binary. So going back to before when we looked at the inspect output for the encoding on a binary string, let's report encoding binary instead of ASCII 8-bit. This would help a lot of developers realize that what they're working with is a binary string, not ASCII. There is a proposal from about a year ago to make this change that got held up. I'd love to restart that conversation. 2, I think we should remove ASCII compatibility from the binary encoding entirely. And this will absolutely break applications, but I don't think there are really any valid use cases for appending a binary string to a text string. In almost all, if not all those cases, it's a situation where the developer didn't realize they were working with a binary string and it just happened to work. And this is a situation where as long as you're working with ASCII data, it'll work fine and give you the result you want, but the moment you have a byte with the 8th bit set, you get an error, and developers largely don't know how to resolve it because Ruby has made it so easy to work with strings without having to care about the underlying encoding mechanism. 3, I would love to just get away from broken strings. They complicate a lot of things, and there's really no valid use case for them. At the heart of all this, I would like to break apart binary data handling from the string API. And there's a few different ways we can do this. We already have IO buffer. I think we should just use this more. So instead of giving users binary strings, we should give them IO buffer instances and make them have to convert them to strings if they want to append them to string data. But I'd also like to see a simpler type for just working with arbitrary binary data. JRuby has this internal class called a ByteList that I think really encapsulates the functionality we would want in Ruby. The ByteList type would have a much smaller API, so none of the string text stuff that can trip people up. This would also simplify the string implementation, so it will only work with text, and it'll be more efficient for both. On the ByteList side of things, like when we're working with binary strings, they're still strings. So when you append data to them, they need to run through all of the logic strings do to make sure the encodings are compatible before they allow the operation to proceed. Likewise, if you're trying to append byte values, it will admit any integer value, even though you might only want bytes. And I would also love to see it much harder to break strings. So these ones get a bit more controversial, and they do assume that we have some kind of binary type in place first. But deprecating setByte, this really is only used if you want to use strings as a binary buffer. If we had an alternative to that, I don't see there being a valid use case for this. And again, it kind of confuses Rubyists because it's there and it makes it look like this maybe is something you should use when working with text. And I'd like to deprecate force encoding. Now this one's a little harder because this has a very valid use case. Currently, if you get a binary string, like if you're reading a UTF-8 file from disk in chunks, the resulting string will be a binary string even though you know all the data is valid UTF-8. And force encoding allows you to replace the encoding without changing any of the bytes. But I've found on teams I've worked on and other people I've talked to that people that don't really understand when encodings break use force encoding as the wrong tool to fix it for two reasons. One, it doesn't raise an exception, so it looks like the right thing to do, or they think it's just a faster way to transcode. And as a result, it ends up corrupting or losing data in the process. All right, so to recap, Ruby strings are remarkably complex under the covers. They're difficult to optimize right now because they have two conflicting use cases. If we made strings really just oriented around text, then we could optimize them using different underlying representations. But by splitting the two of them, we can also make it much harder for developers to inadvertently break data. Broken strings, I think, are always a logic error, but I'll leave open the possibility there are use cases I don't know about. But because we lazily compute the code range value, and sometimes we raise an exception, and other times we don't, it makes it hard to tell when a broken string is introduced in the system, and I think if we made that a more eager process, it would help developers figure out where their logic error is. Having the presence of broken strings actually hinders optimizations. So there are ways to calculate the length of a UTF-8 string without having to look at every byte. Because we can't know if a string is broken or not. In Ruby, we do have to look at every byte. So if we got rid of broken strings, we could have faster text in the more common case. And then a proper binary interface, I think, would be beneficial to everyone. It would greatly simplify the string API. It would fix this kind of leaky abstraction and allow us to play with other ways, whether it's ropes or some other mechanism, to optimize text data for things like web templating engines and such. It would normalize encoding logic. We wouldn't have this one special case encoding that doesn't map to characters. So if we got rid of the ASCII 8-bit encoding entirely, then the encoding logic would be easier. And it would just be faster and simpler for working with binary data. All right, this is just a slide of some resources if you're interested in more of the background. And thank you for your time.